Hi guys, good afternoon. So in the last session, we have seen about cryptography, like how confidentiality, integrity works. Okay, what are encryption algorithms, what are hashing algorithms, all these things we have seen. Now we need to understand about IPSec. So IPSec stands for Internet Protocol Security or IP security, you can say. I haven't received the recording yet for last two class. Have you submitted the form? Yesterday, everybody has received the access, right? I had shared with everybody. Please check your email, okay? And if you don't find it in your email, in that case, just go to Google Drive, and in the Google Drive, you'll have a shared with me section. Okay, see here how you will access it. If you don't find an email, sometimes happens that you're not getting an email. So just go to your Google Drive. In your Google Drive, you'll find this shared with me section. When you will go here, you'll automatically find VPN batch 75. Okay, clear? All right. So what is IPSec? IPSec is a framework of protocols and open standards. So IPSec is not a single protocol, it's a collection of protocol or suite of protocols. Okay. So the main objective of your IPSec is to provide a set of cryptographic methods to protect IP packets at layer 3. Okay. Now, most commonly when we talk about IPSec, we generally say that it is used to provide security to your VPN tunnels. But this is not always the case. Okay, IPSec is a suite of protocol that is used to protect your IP packets at layer 3. Anywhere you can implement it to encrypt your traffic. But yes, in most cases, we say that, okay, it is used in the VPN cases. Okay, so IPSec is not a single protocol, rather it is a suite of protocol and used to provide these services. What kind of services? Authentication, confidentiality, integrity, and replay protection. Now, what is replay attack? First of all, you need to understand a replay attack if you want to understand replay protection. So what is a replay attack? Okay, Rakesh, if you haven't received, so I'll check it and I'll give it to you again today. What is a replay attack? Hmm? What is a replay attack? Question is about replay attack. No? What is replay basically? Playing again. But in the replay attack, this thing doesn't happen. Replay attack simply means one source and destination are communicating. Somebody in between is sniffing the traffic. And then the hacker or the person who is sniffing the traffic, they are using the same captured packets to establish a connection. That means they will resend the same packets, whatever they have captured, same packets they will resend. Okay. So your IPsec provides, like, for example, what happens, let's say, you can consider like this is one source, this is one destination, and they are connected via internet. Okay. Now, this is the initiator, we can say, or sender, and this is the responder. These are the two terms that we will be using in the VPN, initiator and responder. Now, let's say this guy is initiating a tunnel setup. So somebody in between, there's a hacker Okay, this is a bad guy who is sniffing all the traffic. Okay, so he will capture all the packets, but these packets are also going here. Now this guy has established a tunnel here. The tunnel has been established. Now what the hacker will try to do, hacker will also try to send the same packets. So that hacker will think that, okay, I will also establish a secure tunnel with this guy. Why? Because whatever the packets he has captured, same packets he is delivering this side. So the protection from these kind of attacks is also provided by your IPSec. Clear? Okay. Now IPSec can be configured without IKE, but IKE enhances IPSec by providing additional features, flexibility, and ease of configuration for the IPSec standard. So if we talk about your IPSec, right? So your IPSec, so you can see this diagram here that it is a collection of these three protocols like IKE, ESP, and AH. Okay, so these two, ESP and AH, these will be used for the communication. Okay, like if we talk about, basically you can say like these are the headers. These are what? Headers. So let me show you one book. Multiple things are there. To make it clear. You have done routing switching, right? So you have Encore NRC books. Did you go through the books? No, right? Chapter 16, overlay tunnels. Here, IPSec. Now see here. IPSec is a framework of open standards for creating highly secure virtual private networks using various protocols and technologies for secure communication across the insecure networks, such as internet. So IPSec tunnels will provide you security services which are listed in, say, like this kind of peer authentication, confidentiality, integrity, and replay detection. Okay, so replay detection will do what? Prevent man-in-the-middle attack, where an attacker captures the VPN traffic and replay it back to a VPN peer with the intention of building a illegitimate VPN tunnel. So this will be provided, like this is what they will try to do, what the attacker will try to do. And what your IPSec will do, IPSec, in case of IPSec, every VPN packet is marked with a unique sequence number. Okay. And a VPN device keeps track of the sequence number and does not accept a packet with a sequence number it has already processed. That means here in this case, when we were talking about the example, that this guy initiator has already established a tunnel right here. So whatever the packets were exchanged, that sequence number is already processed. So if he will try to send it again, this responder will say that, okay, this packet is already processed. Why this is coming again? So it will drop the packets. This is how your replay protection will be provided. Okay. Now, IPSec uses two different packet headers to deliver the security services. What are those? AH and ESP. So if we talk about AH, your authentication header, this will provide only data integrity and authentication. Your AH will only provide what? Data integrity and authentication. That means with the help of AH, you have access to hashing algorithms. AH will not perform encryption. If no encryption, that means no confidentiality, right? If we talk about AH, so it will support only hashing. Hashing means only integrity and authentication will be done, but confidentiality is not there. And if we talk about ESP, ESP will support both encryption as well as hashing. That means confidentiality also, integrity also, authentication also. So then you might have a question that, okay, why do we go and use AH then. Why do you want to use AH? Sometimes what will happen that you might want to monitor the traffic. You might want to monitor the traffic that, okay, what is the traffic passing? Now, if encryption is there, your data will get encrypted. You will not be able to read that, okay, what is going on inside the tunnel. What is going on, we will not be able to read. But when we use AH, in that case, what will be happening? Your data will not get encrypted. And if your data will not get encrypted in that case, you can easily see the data. This is clear. So see here, your IP authentication header provides data integrity and authentication and protection from hackers replaying packets. That means replay attacks are prevented here. But the authentication header ensures that the original data packet has not been modified because of the integrity during the transport on the public network. It creates a digital signature similar to a checksum only, okay, to ensure the packet has not been modified. And what is the protocol number for AH? 51. And for ESP, it will be 50. See, ESP 50, AH 51. Okay. Now, the authentication header does not support encryption. That means there is no data confidentiality. And also there is no NAT traverse. Okay, so right now you guys don't know what is NAT. We'll come to. Okay. And for this reason, it is not recommended unless authentication is all that is desired. That means you do not use it in the real networks. If I want to establish a tunnel, that means I want a secure communication. And for secure communication, I should maintain what? Confidentiality also. With integrity only, it's not sufficient. Otherwise, if I'm maintaining integrity only, if I'm using AH only, my data is still traveling in the clear text. And then what? Anybody will be able to capture it. Understood? So that is the reason we go with what? ESP. ESP stands for Encapsulating Security Payload. So it provides data confidentiality, authentication, and protection from hackers replaying packets. So typically, a payload refers to the actual data minus any header. What is a payload? Whenever we say, right, whenever we see packet flow, we always say source IP, destination IP, source port, destination port. Then we go to the payload. So payload is what? Your data without any sort of headers. So here, that is the same thing it is telling you. That payload refers to the actual data minus any headers. Okay. But in the context of ESP, the payload is the portion of the original packet that is encapsulated within IP header. Okay. So basically that means what? That inside IPSec header, anything that is there, that is a payload. Okay. And we will see this thing because ESP has two modes, tunnel mode and transport mode. Okay. So ESP ensures that the original payload, okay, your original payload before encapsulation, it maintains data confidentiality by encrypting the payload and adding a new set of headers during the transport process. So see here, this is the original packet. This is the original packet. That means it has a data and it has a original IP header. So what ESP will consider? We have two modes, tunnel mode and transport mode. So first of all, in the transport mode, what is happening? That this is data, this is original IP header. So your ESP is what? Encapsulating what? See here, ESP encrypted data is what? Only your data. Your original IP header is still here. Are you able to understand this? That out of this message, this is the original packet, only this data part is getting encrypted. And in the tunnel mode, what will happen? See here, your original IP, original data, everything will get encapsulated. This is clear. So this is the default mode. Your tunnel mode is the default mode. So you will see in the tunnel mode, it will encrypt the original packet, entire original packet. And then it will add a new set of IPsec headers. That means whatever the data is there, whatever the original IP address is there, everything will be encapsulated, and above that new IP header will be attached. Okay. And in the transport mode, encrypt and authenticate only the packet payload. That means only your data. So overall difference here between the tunnel mode and transport mode is what? That in the tunnel mode, entire packet will get encapsulated. Whatever the packet is coming, entire packet will get encapsulated. And in a transport mode, only your data will get encapsulated. Only your data will get encapsulated. This is clear. And then we have seen that, okay, for encryption, we can go with the DES, 3DES and AES. And for hashing, MD5 secure hashing algorithm. Then this is Bepi-Hellman for key exchange. Okay. Then for authentication, we have methods like pre-shared keys or RSA signatures. So RSA signatures, this will be using what? The public key, that is digital certificate. Remember yesterday we were talking about the certificates. So they will be using what? Certificates for authentication. And this is pre-shared key. That means we will define a password. We will define a key. And this key we have to configure on both the sides. Okay. So a security mechanism in which a locally configured key is used as a credential to mutually authenticate the peers. Is that clear? Okay. Yeah, that ESP will add both the things. Adder, trailer, authentication, everything will be added. That will happen in both the cases. Yeah, both the cases. But in case of transport mode, it is adding only in front of the data. But here, entire packet. If you understand here, see, this is my original packet. Out of this original packet, my ESP is encapsulating here which part? Only the data part. My original IP header is outside the ESP. Right? But here, see, in case of tunnel mode, what is happening? Same packet. This is the same information. So that means this entire IP header is getting encapsulated. And after that, your IPsec is attaching a new IP header. Is that clear? So this is the default mode. That is your tunnel mode. Which one? Yeah, both. See, if original IP header has been encapsulated, so for packet routing, new IP header will be required, right? Without IP, how the packet will be routed? Cannot be routed. So that is the reason it is attaching. And here what is happening? Only data is encapsulated. So your original IP is already there. No need of, right? There is no need of any new header. Practically, we will see all these implementation, tunnel mode, transport mode. There you will see that sometimes we will even have three IP headers. Then we have to remove some of them, right? This is clear. So overall, right now, basic difference, what you need to understand, that in tunnel mode, entire packet will be encapsulated. In case of tunnel mode, your original entire packet will be encapsulated. In the transport mode, only your data will be encapsulated. Clear? Authentication. We say, right, your VPNs, they will provide what? Authentication also. So this is authentication. Clear? All right. Transform set, we'll come to it. This will be in the phase 2. Okay. Now we say that we have see ESP we have seen AH. Now it's time we see about I. Okay. Internet key exchange. So this is a protocol that performs authentication between two endpoints. Okay. To establish what? Something known as security association. Now, what is a security association? So a security association is basically a number of parameters. Okay, we generally call them those parameters. We generally call them what? Haggle parameters. Okay, see here. Those parameters, we call them Haggle. Okay, so what is Haggle? H stands for hashing. A stands for authentication. G stands for DH group. Okay, Diffie-Hellman group. E stands for encryption. L stands for lifetime. So this group, this is known as what? One security association. So basically, in a security association, we will define all these things, that which hashing algorithm has to be used, then which authentication method, whether pre-shared key or RSA signatures you want to use. So in most cases, we will go with the pre-shared key only. Then after, which DH group you have to use, which encryption algorithm, what should be the lifetime. Okay, so these all things we are going to see. Okay, these all things you will be defining in what? A security association. Okay, so this is what? This is a security association, or in short, we will call it as an SA. Here, now, see here. This is also known as IKE tunnel. So these security association or tunnels, these are used to carry what? Control plane and data plane traffic. So when we will use IKE, so in IKE, we have two versions, version 1 and version 2. In both the IKE version 1 and version 2, we will have two phases, phase 1 and phase 2. Okay, so the phase 1 will be known as what? Control plane, and your phase 2 will be known as what? Data. Phase 1 will be control plane and phase 2 will be data plane. So data plane means actually your data will be transferred. So in which phase it will be transferred? Phase 2. In phase 1, you will only exchange the keys and you will perform the authentication. Okay. So there are two versions for IKE, which is IKE version 1, RFC number 2049, and IKE version 2, which is RFC number 7296. Okay. And these RFCs, see, when you are going to the interviews, you can mention about these RFCs. Okay. See, what is an RFC? Book. What is the full form of RFC? Hmm? Hmm. Forgot. RFC stands for request for comment. Okay. So these are the documents in which your protocols are defined. That means these are individual documents about a single protocol. So like IKE version 1, RFC number 2049. Okay. So what you can do is you can go on the internet, and here you can search for RFC 2409, which is IKE. Now this is your protocol that is defined in almost 30 pages. Now, one way is you can go and read this entire document. This will be a kind of text document only. If you want to download it, you can even download it also. Okay. So, here everything about the message exchange, you can see main mode, aggressive mode. Okay. So Diffie-Hellman key exchange, every single thing will be there. Okay. So sure. See that there will be initiator, responder. So like this, they will explain everything. Now the thing is that maybe you're not very interested in reading this text document, right? So what you can do is you can go and we all have a tool, correct? And here, say RFC 2409. Okay. and you can say explain. Instead of reading 30 pages, read this summary. Phase 1 main mode, phase 2 quick mode. These are the exchanges, algorithms, security, updates. Okay, see here, this is 7296, which is about IKE version 2. Okay, so now if you want that, okay, here something is there about the exchanges, you want to learn more. So you can say something like, no, according to RFC 2409, explain the message exchange. Okay, now what is the message 1, message 2, every single thing will be there. So this way, see, you got an overall idea what is there in the IFC. Now, what is there in the RFC. Now what you can do is when you're going to the interview, you can include just one extra word in your answer. That according to this RFC, this is the explanation. Although you're going to explain the same thing only. They are going to, let's say if somebody is asking you about, let's say, what is the IKE1 message exchange. So one is you will directly start telling that, okay, this is the first message, this is the second message. There are two modes, main mode, aggressive mode in the phase 1, then in the phase 2, quick mode is there, right? So main mode and quick mode, total 9 messages. Like this, you will start explaining. But if you add this word that according to this RFC, now this will highlight automatically that, okay, you have studied it, although you haven't, right? So this makes a lot of difference. This is clear? Hmm? Similar what? Your answer will be eventually the same only. Just in the beginning, you are using one extra word that according to RFC 2409. Now that guy, even he don't know, if the guy don't know, let's say what is the RFC 2409, he has to search. And if he will search, he will get the same thing. That makes a lot of impression, right? That can make a significant change in your interview decisions and your package, right? So this is how you can do. And also do not neglect your books. They are having everything in very simple manner. From CCNA to CCI, you have got a lot of study materials, but we barely open the document section. Just go through a video section. Okay, this is today's video. Follow the same video, follow the same practical. That's it. Okay, so these things you should not do. Okay. So the IKE version 1 specified in the RFC 2409 and IKE version 2 specified in the RFC 7296. So IKE version 2 was developed to overcome limitations of IKE version 1 and provide many improvements over the IKE version 1's implementation. For example, it supports EAP, that is certificate-based authentication. Okay, has anti-DOS capabilities, need fewer messages, like in case of if you are going with IKE version 1, so always you will go with the main mode and quick mode. Total 9 message exchange will be there. Okay, but in IKE version 2, you will see like 4 message exchange. Okay, then after needs fewer message exchange to establish an IPSec essay. So understanding your IKE version 1 is still important because some legacy infrastructure have not yet migrated to IKE version 2. Okay, and they have devices or features that don't support IKE version 2. So that's why you still have to learn what version 1. And in the version 1, always we will go with main mode and quick mode. Okay, so this is the IKE version 1. Your IKE internet security, your IKE uses this protocol. Okay, ISACAM, Internet Security Association Key Management Protocol. So this is a framework for authentication and key exchange. So like I said, in IKE, first phase will be what? About key exchange and authentication. Okay, between two peers to establish, modify, and tear down the security association. And what is a security association? This is an essay. Okay, so it is designed to support many different kind of key exchange, and ISACamp will use UDP port number 500. This thing you must remember. Okay, that it will use UDP port number 500. Later on, I will also tell you that it will switch to UDP port number 4500. Okay. Now, we have two phases. Okay, that is phase 1 and phase 2. So phase 1 will do what? It will establish a bidirectional security solution between IPers. It is also known as ISACamp. It's also known as ISACamp. And because the SA is bidirectional, so once it is established, either peer may initiate the negotiation for phase 2. Anybody can initiate. Okay, but see, by default, like I said, there will be two entities. One will be the sender. Like two sites are there, site 1 and site 2. So there are two roles, initiator and responder. So anybody can be initiator. It is not fixed. Anybody who will initiate the tunnel setup will become the initiator. So for phase 1 negotiation, it is mandatory that, okay, you will initiate the traffic, that site will become what? Initiator. Okay, and the other will become what? Responder. But once your phase 1 is established, either peer may initiate the negotiation for phase 2. Okay, so phase 2 establishes unidirectional IPSec assay leveraging the ISACamp assay established in the phase 1 for the negotiation. See, for phase 2 negotiation, it is important that your phase 1 negotiation should be successful. Without successful negotiation of your phase 1, there is no phase 2. Yes, once phase 1 negotiation is done, phase 2 negotiation is done. After that, even if phase 1 goes down, no problem. Because there is some amount of lifetime we have, that how long that will be valid, the keys will be valid. So the default lifetime you can note down, okay, that for phase 1, it is what? 24 hours. Okay, in seconds, it is 86,400 seconds. Yes. And phase 2, it is 1 hour, which is 3,600 seconds. Okay, these are the default. Why phase 2? Tell me. Yeah, phase 1, 24 hours. What if somebody got to know about your keys? Right? So that's why phase 2 will be negotiated again after 1 hour. And when phase 2 lifetime will expire, there will be no negotiation of phase 1 again. Okay, because still the lifetime is 24 hours. That means phase 1 is still up. But if anytime phase 1 is going down and then renegotiation of phase 1 is happening, so in that case, your phase 2 will also be renegotiated, even if the lifetime is there. Doesn't matter. Okay, so I'll show you all these situations. We will create different scenarios that, okay, phase 1 went down, phase 2 went down. Okay, so in those cases, what will happen? Practically, we will understand all these things. Okay. Negotiation means agree about, like, what you're asking. Who? Phase 1 or phase 2? Phase 1, see, they are negotiating these security association. That means agreeing on the protocols, what they will be using. Okay. So here you can see phase 1 negotiation can occur using the main mode or aggressive mode. So two modes we have, but always we will go with the main mode. Okay. The peer that initiates the negotiation process will be known as the initiator, and the other peer will become what? Responder. Okay. Now your main mode will consist of how many messages? 6 messages. So total 6 messages will be there. MM1 means main mode message number 1. This is message number 1. Then we have message 2, 3, 4, 5, and 6. Okay. Then after phase 2, this is about the aggressive mode. Right now, let's not come to it. This is the phase 2. So in phase 2, there will be 3 messages exchanged. In phase 2, how many messages will be exchanged? 3. So total, how many messages? 6 plus 3, 9. And when you're going with the aggressive mode, so aggressive mode is having 3 messages and quick mode is having 3 messages. Total 6 messages. This is clear. Now understand it in short here. Okay. We have IKE protocol. IKE has 2 versions. Version 1, version 2. In the IKE version 1, we have 2 phases. Phase 1, phase 2. Okay. So phase 1 is known as what? ISACamp assay, and phase 2 is known as IPSec assay. Clear? Now, if we talk about phase 1, this is IKE version 1. In the IKE version 1, phase 1, it has 2 modes. Main mode, 6 message exchange is there, and aggressive mode, 3 message exchange is there. And in the phase 2, we have quick mode, which is having 3 message exchange. So now you might have a question, can we configure both the modes, main mode and aggressive mode? No, you cannot configure. You can have only one mode. Either you can have main mode or you can have aggressive mode in the phase 1. Phase 2 is mandatory. For data transfer, phase 2 will be mandatory. Okay. Yes. So this is where your data transfer will be there, and this is where your key exchange and authentication will be there. Is that clear? So keys will be exchanged in the phase 1, and data will be encapsulated and encrypted in the phase 2. Okay. This is clear. So either you can have this scenario. That you are using this combination, main mode, 6 messages, quick mode, 3 messages. So total, how many messages? 9 messages. Or else you can go with aggressive mode and quick mode. So total, how many messages? 6 messages. Now, why we do not use aggressive mode? In the aggressive mode, data is insecure. 3 messages are there, but everything is in clear text. So if everything is in clear text, anybody can know. Okay. And here it is secure. Yes. Whatever the negotiations will be shared, everything will be in the clear text. Let me show you. See here. Yeah, this is the first phase, aggressive mode, right? Aggressive mode consists of 3 message exchange, and it takes less time, okay, to negotiate the keys between the peers. However, it doesn't offer same level of encryption security provided by the main mode negotiation. Why? Because the identities of the 2 peers trying to establish the security association are exposed to eavesdropping. So anybody who is sniffing the traffic, they will be clearly able to see the identities. Because of these messages only your tunnel is getting established, right? So all the information, your authentication, your keys, your identity, everything is shared in these messages only. Everything is shared in these messages only. Okay. So like you can see here, main mode message number 1, 3, and 5, whatever the details are being shared, it is shared in one message only. And same way, 2, 4, and 6, they will be shared in the second message only. Okay, so what are the details exchanged in your main mode message number 1, 3, and 5? See, 2 people will be there. One will be the initiator, one will be the responder. Correct? 2 entities are there. Consider this is initiator. This is the responder. Okay. So first message, let's say this becomes an initiator. So this is the main mode message number 1, where it will be sending the security association information. So second message, main mode message number 2, So this guy will tell that, okay, these are the security association I have. You can have more than one. That means this guy will send all the security association, whatever you have configured. This guy will say, okay, let's go with this one. This guy will select one. This is how they will negotiate. Okay. Then after, same message number 3 will be there. Okay. So these are auto-generated messages. 3 and 4. These are auto-generated messages. And number 5, where the authentication will happen. And number 6, where the authentication will happen. So message number 1, 3, and 5. These are given by one guy, initiator. And message number 2, 4, and 6, these are given by responder. So in one message only itself, it will send all the things. And same way, responder will also send everything in the one message only. And after that, finally, one message will be there for authentication. Is that clear? Now, let's first of all understand what are the things that are being exchanged in the 6 messages. Okay. See here. Main mode message number 1. Here, what is happening? This is the first message that the initiator will send to the responder, and one or multiple essay proposals are offered. You can configure one, you can configure more than one. Okay. So the responder needs to match one of them for this phase to succeed. That means initiator will be giving multiple essay options to the responder. That, okay, I have all these options. Which one you want to select? And the responder will select one. So what are the things we are sharing? The essay proposal will include different combination of hashing algorithm, encryption algorithm, authentication, Diffie-Hellman, and lifetime. And you can see what is the default lifetime, 24 hours. So here the initiator is sending all this information. Okay. This is the initiator. This is the responder. So in the message number 1, this guy is sending all these informations. Correct? Now what? Message number 2. This message is sent from the responder to the initiator with the essay proposal that is matched. So this guy has given all the essay options, that essay 1, essay 2, essay 3, multiple essay it has given. And this guy will say, okay, let's go with this essay 1 only. Understood? So they have agreed on these parameters. Once they have agreed, now what? Message number 3. In the message number 3, what will happen? The initiator will start the DH key exchange. The Diffie-Hellman key exchange will happen. So in the message number 3, key will be exchanged, and same thing message number 4. The responder will also send its own key to the initiator. So both initiator as well as the responder, they are exchanging what? They are exchanging the keys. Once the key is exchanged, then message number 5, the initiator will start authentication by sending the peer router its IP address. This guy will send its own IP address. Okay, so here what will happen? Authentication will happen. And in the message number 6, this guy will send its own IP address for authentication. So message number 6, the responder will send back a similar packet and authenticate the section. And at this point, your phase 1 will be established. Your ISACamp assay will be established. This is clear? Yes. What if? See, we can have multiple essay because, see, it is not necessary that I have an initiator here. So this guy might be having different tunnels, right? Might be connected to different locations, right? So for this location, I might have a different algorithm, different set of algorithm. So this is why we can have one or we can have multiple also. Totally fine. One essay will be. See, even if this guy is sending multiple, eventually this guy is selecting only one. The responder will select only one. And we will see practically this thing also, that we will send multiple essay and the responder will use only one. And in this also, we will use different combinations. How? Like what kind of different combinations we will use? Understand here. See, in the phase one, what we are sharing, hashing algorithm, encryption algorithm. So we will create two different, let's say two different essays, one with the DES algorithm, another one with the AES algorithm. Now we will see which one they will select, lower encryption or higher encryption. So that kind of possibilities also we will see. And definitely we know that AES they will select. Clear? Okay. These are the 6 messages exchanged. Now, here we have screenshots of all these things. So let me show you. This is about, we have seen that phase one is known as what? Your control plane, and phase two is known as what? Data plane. And in the IKEv version one, we have phase one, phase two. Phase one is known as what? ISACamp assay, and phase two is known as what? IPSec assay. And your ISACamp will use the UDP port number 500. But like I said, sometimes what will happen? 4500. So in which case this will happen? This will happen when you have translating device. That means what? This is site 1, this is site 2. Right now, between site 1 and site 2, there is no translation device. There is no translating device. So if there is C, if there is no translating device, will the IPs change? There is no change in IP. So what will happen? The hash value will remain same on both the sides. The hash values will be same on both the sides. But if you have any firewall here, let's say, for example, consider ASA, and this will perform the translation. Packet header got modified. Header modified, that means checksum modified. Now what? Not matching. So this will show support for NAT-T. This will show support for NAT-T. That means if there is a translating device in between, okay, we will see two concepts. See, NAT-D and NAT-T. Two different concepts are there. NAT traversal and NAT discovery. Okay, so this NAT-T support, it will be checked using the VID payload, vendor ID payload, which will be exchanged in the phase one. What happened? Confused? Vendor ID payload. Okay, let me show you in screenshot first. Otherwise, you will get confused. See here. This is a screenshot of your IKEv version 1 main mode message number 1. Okay, and we will also capture the packets when we will see it. See here. First thing you will see here is what? That source IP, destination IPs. And what is the source port and destination port here? 500. That means ISAC. Okay. Now we will have SPI parameters. Okay. So in the message number 1, the SPI, initiator SPI will be there. Responder SPI will be 0. So what is an SPI? Security parameter index. So this is a value that is randomly calculated. And in one VPN communication, okay, this initiator SPI and responder SPI will remain as it is. See, right now, first message is there. So initiator is sending. That's why we have initiator SPI. Responder is, we don't have any idea. That's why responder SPI is 0 here. But when the responder will send a message, there what will happen? This responder SPI will also be there. Okay. But there it will not happen that initiator will become responder and responder will not become initiator. No. Their roles will be defined already. That means this is going to remain same, and your responder SPI is going to remain whatever the new value responder will give. Okay. Then this is the information about version, your IKEv version. And here, the first payload we will have is what? Security association. Inside the security association, what kind of payload we have? Proposal. Okay. And how many proposals are there? That also you will be able to check that how many proposals are there. And inside the proposal, we will have what? Transforms. Okay, your payload will be what? Transform payload. Inside the transform payload, you will be able to see all the attributes. So if you see here, inside the transform payload, if you will see here, there you will be able to see whatever we will configure. What is the encryption algorithm? What is the key length? What is the hashing algorithm? What is the DH group? Okay. What is the authentication method? And about the lifetime, the haggle. This information will be there in the first message. So this is clear. Okay. Now, same thing here. The message exchange are displayed. This is the first message. And see, in the first message, like I said, your initiator SPI will be there, responder SPI will be. But in the second message, you check. Responder SPI will also be there. And initiator SPI will not change. See here. We have some value E2, D6, something like this. And same value is here also. So it will not change. That means if you are initiator, you will remain initiator only. And if another one is becoming responder, it will remain responder only. Is that clear? Okay. Now see here. In the first message, one thing, your SPI parameter will be there. In the first message, your SPI parameter will be negotiated. This is the first message, IKEv1 message exchange. So here, SPI parameter. Other than that, the haggle will be exchanged. Clear? Same way in the second message, this guy will have a SPI and he will agree on the haggle. The responder will also agree on the haggle. Then message number 3, the DH key exchange, Diffie-Hellman key exchange. And here also Diffie-Hellman key exchange. That means both initiator and responder, they will exchange their keys. Okay. And then message number 5, authentication with encryption. So these 4 messages, message number 1, 2, 3, and 4, they will not be encrypted. And from message number 5, your encryption will start. That means after this, we will not be able to see the information. Because in the message number 3 and 4, what is happening? If you see message number 3 and 4, key is getting exchanged. Once the encryption key is exchanged, now encryption can start. Now encryption can start. So they will start encryption. But now you will say, if these messages are not exchanged, anybody can sniff this key. Anybody can sniff this key, then how your DH is secure? Correct? So let's understand how your DH will, how they will, like with the help of DH, how the initiator and responder will calculate their keys and how they will agree on the same key. Okay. So let's understand it. I'll take help of a diagram. Okay, on Wikipedia, there is a diagram with the help of which we can understand. This diagram you can take as an example. This image, open image in data. Copy. This is not white. See here. So you can consider that this is your initiator. Okay. and this is your responder. Now both initiator and responder, they will generate keys. Okay, so they will generate public keys and private keys because Diffie-Hellman is a asymmetric encryption algorithm. Okay, so let's say this guy is generating a public key. Consider 5 numerical number we'll take, and this guy is also generating a public key. Okay, this is the public key. Public key is freely distributable. Now this guy will use what? Private key. Let's say this guy is creating something like 15, and this guy here, he is creating a private key as a 25. Now private keys, they are not going to share with anyone. Private keys, they are not going to share with anyone. Now here, what they will do before sharing, they will add up this public key and private key. They will add this public key and private key. So that means here, whatever the key I will be exchanging, that will be a sum of 5 plus 15. That means what I will be sharing? 20. And from this side. Now, why I'm adding both the keys? Because if anybody is sniffing in between, they will never come to know which is the public key, which is the private key. Okay. Now, so same thing, once they exchange, they will come here. They have exchanged with each other. Right. Now, both of them, what they will do, they will add their private keys again to the same thing. So 30 plus 15, right? Like here, what is the private key? Private equals to 15. And here, what is the private key? 25. Now add both of them. So this is the new key. What is the sum? 45. And what is the here? See, they have the same key. New key will be 45. So if somebody sniffed this key 30 and 20, so even if they will try to add, what the new key will be? 50. Let's say in here, when they were transferring this information with each other, when they were sharing this information, somebody captured it because this is the part that is traveling through the public transport. So now if somebody will capture also, it will be 50. Hmm? They did not share the private key. So they didn't share. They just combined both the public key and private key, then the sum they shared. So if you are having 20, now this can be 19 plus 1 also. This can be 19 plus also 1 also. This can be 2 plus 18 also, right? So that means actual key nobody will come to know. Same way this guy is sharing 30. Now this can be 1 plus 29, 2 plus 28, 3 plus 27. How they will come to know? And once they capture both the keys also, eventually 30 plus 20 is what? 50. Again, it's not the correct key. But with the help of DH, what happened? That your initiator and responder, they were able to agree on a single key. Now this is the same key. This is the same key. So now if this key is same, it becomes asymmetric encryption. Yes or no? And now your initiator and responder, they can start encrypting the data packets. Because in the masses number 5 and 6, they will be sharing their identities. And those identities we want to protect. And that is the reason from masses number 5 itself, your encryption will start. This is clear? Yes or no? Online people? Hmm? This is masses number 3 and 4. Yeah, this is your message 3 and 4 from message number 5, because in the message number 3 and 4 the keys have been exchanged. So both of them have calculated the key that okay, this is the new key. Now they will use this key to encrypt the traffic. Okay. See here. The initiator will start now what? The authentication by sending the peer router its own IP address, and this guy will also send the IP address for authentication. So this is how the message exchange is there in the phase 1. Okay. So how these DH keys and all they look like, if you want to see. So this is the message number 1, where initiator SPI is there, responder SPI is 0, then initiator is sending this SA, security association. In the message number 2, what happens? The responder will agree on it that okay, this is the SA we are going to use. Message number 3. Now see here. In the message number 3, what will happen? Initiator and responder SPI is as it is. You can see here. Initiator SPI, responder SPI is as it is. Okay, whatever initiator SPI was there, E2 D6, same initiator SPI is there. Okay. Then the key exchange. So this is the key exchange data, and it will be a very large key, depending on the what DH group you use. So 1, 2, and 5 we try to avoid. Okay. Like normally 1 and 2 you will avoid. Then you can start using from 5, 14 like that. Okay. So this will be the key. And along with the key, there is something called as nonce value. Okay. See here, NONCE. What is nonce? Full form for nonce is, see, this is the word here, nonce. Stands for number used once. Okay. So this is a random number. This is a random number that your initiator will generate. This is a random number that your initiator will generate. And it will send this nonce value with the key. It will send what? It will send this nonce value with the key. Okay. So why this nonce value is sent? So that when the responder is responding, the responder has to use the same nonce value. Responder has to use the same nonce value. So like here, nonce I'm using what, 10. So the same the responder has to give me back. Then I will understand, okay, this is the correct data. And if this nonce value is changed, that means this key is incorrect. This is coming from somebody else. And I will not accept it. This is clear. So in the message number 3, your key will be exchanged, your nonce value will be exchanged, and your NAT-D payload will be exchanged. Now, what is NAT-D? NAT-D is for NAT discovery. NAT-D is for NAT discovery. So how NAT discovery will be performed? How your NAT discovery will be performed? So in NAT discovery, you see there are 2 payloads, NAT-D and NAT-D. One is for the source and second one is for the destination. Okay, one is for the source and second one is for the destination. So in these NAT-D payloads, there will be a, see here, there will be a value which is from RFC 3947. Okay, so first of all, understand the difference between NAT-T and NAT-D. NAT-T is for NAT traversal and NAT-D is for NAT discovery. Okay, so See here, detecting support for NAT. So the NAT traversal capability of a remote host is determined by an exchange of vendor ID payload. So this vendor ID payload, it will be exchanged in the first two messages on message number 1 and message number 2. So what is this vendor ID payload? Vendor ID payload will show support for NAT-T. That means both here will agree that, okay, do we support NAT-T or not? Okay. So both of the peers, they will agree on it in the message number 1 and 2. Okay. Then in the message number 3, you saw that, okay, this is the RFC 3947. Okay. So the vendor ID payload for this specification must be sent if supported. If both are saying that, okay, I also support NAT-T, and responder is also saying I also support NAT-T, then what will happen? They will use this RFC, and this is the hash value. This is the hash value. That means this is the value that they will be sharing. This is the value that they will be sharing. So here what will happen? That it must be received by both sides for NAT's traversal probe to continue. That means they are trying to check NAT traversal. That means they are supporting NAT-T or not. So once they agree on that, whether, okay, NAT-T is supported or not, NAT-D will be used to discover whether a translating device exists or not. Whether or not a translating device exists or not. So how it will be checked that whether is there a translating device present or not? So they will be sharing what? Hash value. So like I said, two hash values will be there, one for source, one for destination. How those hash values will be created? Source hash value will be calculated based on source IP, destination IP. Sorry, source IP, source port. And destination hash value will be created based on destination IP, destination port number. In a message, we use source IP, destination IP, source port, destination port. So both the source entities, source IP as well as source port, that will combine, they will make what? Your source checksum. And destination IP and destination port, they will make up what? Your destination checksum. Same way when the other guy will reply. Okay, understand this thing. Let me use a paint file to explain. This is site 1. This is site 2. And they are connected via internet. This is site 1. This is site 2. Okay, and this is your ISP. Now, when they're establishing the tunnel, so we know that there will be source IP part, destination IP part, source port, and destination port. Okay, so when the site 1 will send your message number 3, in that it will use a checksum. In that, what it is going to use? Checksum. So in the checksum, there will be one for source, another one for destination. Okay, so you can consider, let's say here the IP is, for example, 10.1.1.1, and here the IP is 10.1.1.2. Okay, just consider like this, and this is the request message that we will generate. Source IP, destination IP, source port, and destination port. So 10.1.1.1, then you can say 10.1.1.2. Source port, what will be the source port? Random, let's say 1, 2, 3, 4. And destination port, let's say, for example, 500. And right now they are going with the ISACM. So let's say source port also 500, destination also 500. In case of ISACM, it will be source and destination 500. Yes. In case of ISACM, it will be both 500. Now, here, this will calculate the source checksum. Okay. So you can say a random source checksum will be calculated here. Okay. That will be a combination of 10.1.1.1. First of all, these two things will be combined, and then they will calculate the checksum. And here the destination checksum will be what? 10112. Clear? Okay. Now, if there is no translation device in between, so when this guy will respond, what will be the source IP? 10112. What will be the destination IP? Source port, destination port, 500. Right? Source port will be 500, destination port also 500. Okay. So when this guy will also calculate source and destination checksum, so here source checksum will be 10112, correct? And destination, that is 10111 plus 5. So what is the thing that if these two checksums are matching, that means no translating device in between. This is how they will understand that there is no translating device available in between. But what will happen from here? Let's say there is a translating device available in between. Okay, this time let's consider that there is a translation device available in between these two devices. We have a translating device. So this is the scenario which is without NAT2. Okay, this is without NAT, and this will be with NAT. And here we are considering that in between these two, you have a firewall. Okay, consider this is a ASA. Okay, and this ASA will translate your IP into, let's say, for example, 100.1.1.1. Okay. Now, when this guy will generate the packet, site 1 will generate the message. So it will have a source IP, will have a destination IP, will have a source port, and will have a destination port. Source IP will be 10111. Destination IP will be 500. Destination, with whom you are trying to establish VPN, right? Site 2. So source port again 500, destination again 500. Okay. So when here this guy will calculate the checksums, source will be, okay, this will be the same thing. Let me copy paste. Okay. Source will be this and destination will be this one. Same. Here it's going to be same. And when this guy will receive this information, because this message will come where? This message will go from here to ASA. ASA will do what? Translation. And when ASA will do the translation, it will become 100.1.1. Okay. So when this guy is receiving a message from 100.1.1.1, when this guy will respond, when the other site is going to respond, source IP, destination IP, source port, destination port. Source IP will be correct 500 and 500. Right? So now when this guy will calculate the checksum for source and destination, so he will say source checksum will be 10112 plus 500 and destination 100.1.1.1 plus 500. Now when this checksum will come here, because IP address, your ASA will change again. Checksum, your ASA will not change. Right? So when they will try to match it, so they will say that, okay, is the destination and source same? Yes, it is same. But what about this? Different. This is how they will discover that, okay, in between two sites, translating device is there. Okay. And in such scenario, what they will do? They will change the port number to 4500 instead of 500. So that means these four messages will be exchanged. Your 1, 2, 3, 4 will be exchanged over port number 500 only. But after that, they will start exchanging the messages on port number 4500. This is when the NAT. So first of all, in the message number 1 and 2, they will agree that do we support NAT or not. So how they will check the support for NAT? They will use a vendor ID payload. VID payload. Okay. By sending this, they will check what? You can say it is used to check support for NAT. Okay. Your vendor ID payload, it is used to check support for NAT. So once both in the message number 1 and 2, they have agreed that, okay, we support NAT. So in the message number 3 and 4, they will perform the discovery. That is there any translating device available or not available? How they will check? By using this hash value. Okay. And once they know that, okay, translating device is there, the port number will change to 4500. And if there is no translating device, in that case, they will keep on continuing on port number 500. This is clear. Okay. Online people. Message number 5. Because up till the message number 4, they will agree. They will check that whether or not translating device is there or not. Okay. Guys, online people, this is clear. How your NAT without NAT concept is there, how with the NAT concept is there. It is important to understand. Otherwise, when you will see the VID payload and I'll say it is used to check support for NAT, you will not understand why NAT, what NAT. Okay. All right. So now from here, what we can say that, in your message number 1, okay. In your message number 1, we have SPI parameters. We have the entire essay, that is your Haggle. Okay. So in message number 1, what is exchanged? See here. Message number 1 and 2. Okay. So message number 1 and 2, what we are exchanging? Haggle, SPI, and vendor ID. Then message number 3 and 4, key exchange, nonce value, and what else? NATD. Okay, and here VID is there to check support for NATD. NATD discovery 3 and 4 discovery we did, right? NATD will be checked for this only, VID. This will show support for your NATD. Okay. See, so many things I can show you. For if you want to see message exchange, I just created this document, not read by. This is the question mode. This is main mode. See here. You can see the essay proposal will be there in the message 1, which is there from initiator to responder. So your encrypt in the essay proposal, your encryption, hashing, Diffie-Hellman, authentication method. Okay, all these things will be there. What is the purpose? To propose security parameters for establishing the IKC. Message number 2, the responder will send it to the initiator, and this will agree on encryption, hashing, and DH group, and it will confirm the authentication method also. Then message number 3 we have from initiator to responder. It will send what? It will send Diffie-Hellman value, that is the Diffie-Hellman keys, and it will use the nouns. Okay. Then responder will do the same thing, Diffie-Hellman and noun. And message number 5, initiator to responder, identity information. So what kind of identity information they will include? IP address, fully qualified domain names, and they will use the authentication data like hashed or encrypted identity. Okay. Once this is done, what is the purpose of this? To authenticate the initiator and prove the identity is genuine. And then same thing will be done by the responder. And what will happen? Your main mode, complete IKEv established. Your phase 1 tunnel is established. This is clear. Quite confusing, right? So we have seen the message number 1, 2, 3. This is the message number 1, 2, 3. And then we have message number 4. So you see here in the message number 4, the guy is sending same nouns value 10. Here it was 10. So here also it is 10. Okay. And then key exchange is being done here. Okay. Once the keys are exchanged here, now message number 5, we will not be able to see anything. This is for identification. So we won't be able to see anything because from message number 5, your data will start getting encrypted. Because in the message number 4, what happened? The keys got exchanged, 3 and 4. So using those keys, now encryption started. So now message number 5 and 6, the data is encrypted. And this is why sometimes we use AH instead of ESP. Right now, see here in the security association, which protocol we were using. So AES algorithm we are using here. Okay. Here also AES algorithm we are using. This is because we will go with the, no, this is phase 1. Okay. Phase 1 will remain same. ESP we will use in the phase 2. So right now here you can see that the data is encrypted. After this, quick mode will come. That is your second, phase 2. Okay. So in the phase 2, we can decide whether we want to use AH or ESP. If we will use AH, we will be able to see the data. If we will use ESP, then we will not be able to see the data. Okay. But in the phase 1, these 2 packets will be encrypted. Why? To protect the identity. You can see here, exchange type is what? Identity protection. Okay. And same thing is here, message number 5. So this is by default tunnel mode. By default tunnel mode. You can see here, right? Transport mode will do what? Only encapsulate the payload only. So that means you will see extra IP headers. But here we don't see any extra IP header. Here we don't see any extra IP headers. In case of transport mode, you will see it. Okay. So when we will go to the transport mode, that there I'll show you also that when you will use transport mode, we will have extra IP headers. How we can save the IP header also. How we can remove, like we will study concepts about SVTI and all. Okay. So there we will discuss all those things. So these are the 6 messages that are exchanged in the phase 1. Then after, tomorrow we'll discuss about phase 2 also. Okay. So this was the phase 1 main mode message exchange. Now today, what do you have to research about? First of all, you have to revise the phase 1 message exchange, and then you have to check about the quick mode. Okay. And then tomorrow onwards, we will start implementing our first VPN. First site-to-site VPN. Okay. Clear? Online people? All right. So now, those who are attending only today, let me share the format with you. Guys, the form link is there in the chat, so you guys can submit. Okay. All right, guys. So I'll see you tomorrow then. Have a good day. Bye bye.